Continuing on physical chemistry, chapter 17, we're in section 8 now. Now we're going to talk about the temperature dependence of rate constants. We said at the beginning of the chapter, remember that the rate constants, they're dependent on both temperature and pressure, but mostly temperature. In fact, you might even say that, so K is a function of temperature here. It's exponentially dependent, so it might double or triple every 10 degrees. So Arrhenius, he derived an equation for temperature dependency. So this is the Arrhenius equation. K is equal to A times the natural number E to the minus EA over RT, where EA is the activation energy. Now this quantity here, EA divided by RT, the units are in energy divided by energy. So the units cancel out. We say this is a dimensionless quantity, which is good because in the exponent, if you're going to take a number to a power, you can't have any units in the power. That wouldn't make any sense usually. So K is going to have the same units as A, obviously. A is actually made from 3 constants. Now the first thing is the collision frequency that we talked about in chapter 15. So like for oxygen, diatomic oxygen, at 1 atmosphere and 25 degrees Celsius, we say ZBB is equal to 10 to the 9th collisions per second, or ZBB is equal to 10 to the 28th collisions per centimeter cubed per second. The second, of course, would be the size of the molecule, and the third one would be the orientation of the molecule if it's not spherical. This will be your probability factor. So A is what we call the pre-exponential factor, or the frequency factor. A is a measure of the collision rate irrespective of the molecule's energy. Now remember, EA is activation energy. This is the minimum energy that the reactant molecules must have in order to form products. You can also call this a filtering factor. So we get natural log of K is equal to natural log of A minus EA over RT. Now here's a graph of K. Remember the rate constant versus temperature. And as you can see, it curves upwards. So it's exponential, not a straight line. So here's a graph of natural log of K over 1 over T. Now this E is a straight line. The slope is minus EA over R. So if EA approaches infinity, then K approaches 0. So 0 is going to be less than the activation energy, less than 330 kilojoules per mole, usually. And 0 is going to be less than or equal to EA, or less than or equal to 80 kilocalories per mole, usually. Now, there are exceptions. Like free radicals, they can have an activation energy of equal to 0. Like let's say you have CH3, a CH3 radical plus another CH3 radical, they'll come together and form C2H6. There's no energy of activation energy. So that's why free radicals are dangerous. So like if you cook red meat with nitrite in it, the nitrite keeps it red, but the nitrite turns into free radicals when heated. So that can be dangerous. Now let's compare 2 temperatures. So we have K1 is equal to A times E to the minus EA over RT1. So we'll call that equation 1 for the first temperature. And then K2 is going to be equal to A times minus EA over RT2. We'll call that equation 2 for temperature 2. Now remember, for a reaction, the activation energy can't change. So we have K1 and K2. These are the same reaction, but at different temperature. So we're going to divide equation 2 by equation 1. So we get K2 over K1 is equal to A times E to the minus EA over RT2 divided by A times E to the minus EA over RT1. So we simplify that, we get E to the positive EA over RT1 times E to the minus EA over RT2. Now, we're going to say K2 over K1 is equal to E to the EA over R times 1 over T1 minus 1 over T2. So we get the natural log of K2 over K1 is equal to EA over R times 1 over T1 minus 1 over T2 is equal to EA over R times T2 minus T1 over T1 times T2. Now, the graph method, it works better since it uses more points. So here's a graph of K2 divided by K1. So this, remember, is the constant is a ratio of the constant at two different temperatures versus activation energy. So as you can see, higher and higher activation energy means a higher ratio of K2 divided by K1. So like in this case, we're going to say T2 is 310 kelvins and T1 is 300 kelvins. So that's a difference of only 10 kelvins, roughly room temperature. And it makes a bigger and bigger difference depending on the activation energy of whatever reaction we're talking about. Now, if we're talking about an elementary reaction, a single step, then Kf over Kr is equal to Kc. Remember, Kf and Kr are the rate constants. Kc is the equilibrium constant. So the natural log of Kf minus the natural log of Kr is equal to the natural log of Kc. So we're going to divide by dt and take the differential. So the derivative of the natural log of Kf divided by dt minus the differential of the natural log of Kr divided by dt is equal to the differential of the natural log of Kc divided by dt. We're going to call that equation 3 for now. So then we have the natural log of K minus the natural log of A is equal to minus Ea over RT. So then we have the derivative of the natural log of K with respect to temperature is equal to the derivative of the natural log of A with respect to temperature is equal to the derivative of the activation energy with respect to temperature divided by RT. So we're going to say the derivative of the natural log of A with respect to T temperature is equal to 0. So the derivative of the natural log of K with respect to temperature is equal to the activation energy divided by R times T squared. We'll call that equation 4. So if the activation energy is equal to 0, the slope is equal to 0, so the rate constant is not dependent on temperature. If the energy of activation is equal to 0, then the derivative of the natural log of K with respect to temperature is equal to 0. But that's a rare case, remember, like I gave you with the free radicals. Substitute equation 4 into equation 3, and we get the derivative of the natural log of the forward rate constant with respect to temperature minus the derivative of the natural log of the reverse rate constant with respect to temperature is equal to the derivative of the natural log of the equilibrium constant with respect to temperature. Then we get the energy of activation for the forward reaction over RT squared minus the energy of activation of the reverse reaction divided by RT squared is equal to the change in the internal energy. I'm not sure why that 0 is there. Oh, the standard state, divided by RT squared. Now we can just cancel out the RT squared. So we get the derivative of the natural log of Kp naught, which means standard state, with respect to temperature, is equal to the change in the Helmholtz energy. Now that'll be, oh boy, divided by RT squared from before. So we have Kc, but not Kp. So we have the energy of activation forward minus the energy of activation reverse is equal to the change in the energy at the standard state for an elementary reaction. So we have energy versus the reaction coordinate, or reaction pathway. So over here, we might have, reactants, products, intermediates. So this height here, this is the energy of activation forward. This height here, this is the energy of reactivation for the reverse reaction. And this difference here, that's the change in the internal energy. Now this is obviously for an endothermic reaction. It's technically the change in U for the standard state, not the change in enthalpy for the standard state, but pretty close. So K is equal to A times e to the minus EA over RT. Remember, EA is the activation energy for the overall reaction. So, for example, let's say we have K1, K2, equilibrium, K2, like a composite reaction. So K is equal to K1 times K2 over K minus 1. So the energy of activation will be energy of action for 1 minus the energy of activation for the reverse plus the energy of activation for 2.